why this is
why can you call it ozone, the O3?
Oh, you mean xenon ozone?
Yeah.
Ozone is
I
just
know it
for
sounds bad. I'm just
ozone. Well, ozone. Well, it's a legitimate question, but ozone is only specific. It's a common name. It's specifically given just to O3 as this for this group. O3.
Okay. Thank you.
I'm thinking of different examples. Whenever you have something in which H2O occurs, I mean, you don't call it like carbon, water, di-water or something, you know. So it's the same reason.
Wondering.
Yeah. So this is now this is just a reverse game. You have this dinitrogen tetrafluoride code. You have 4. Hydrogen bromide. This is actually hydrobromic acid too. When we talk about acids and bases, so you can call this hydrogen bromide or hydrobromic acid. Sulfur tetrafluoride, boron, trichloride.
Tetraphosphorus, decaoxide.
Tetraphosphorus decaoxide. Chlorine, trifluoride, and so on. I think you got the idea, right? Alright, so we talked about ionic compounds, the nature, why they are forming crystals, what force governs the crystal formation. We talked about molecules, their names, so you need to memorize a lot of things. And now, the next part that we are talking about is about the mole. So this is not about memorizing something, but this is something to understand. You need to understand the concept of the mole. Why is it introduced? It is introduced because we want to count atoms. To be able to count atoms. Why is that important? Well, if you have a chemical reaction like here, this is a chemical reaction in which magnesium, this is magnesium, and it burns in air, so there's air around it, there's oxygen around it. And what it forms is a powder here that is called magnesium oxide. Okay, it forms magnesium oxide. Can we somehow predict how much magnesium oxide is produced?
No.
Well, we want to do that. That's why we are introducing this concept of being able to count atoms.
I forgot that.
What we can do microscopically, you cannot count atoms like this, right? There are billions and billions and trillions, gazillions of atoms. You cannot count them, but you can come up with smart ideas to be able to say how many atoms you actually have in a certain amount of a substance. And this is why the mole was introduced. Because what information do we have? What can you do instead of counting? You can weigh matter. You can put it on a scale and determine the mass of a substance. So if you know the mass of a substance and you know the composition of the substance, we will be able to actually even say how many atoms or molecules are in that substance. So we need to be able to convert mass to numbers of particles, to numbers of atoms or numbers of molecules, so numbers of particles. And that's where the concept of the mole comes into the game. So, the mole is, and as usual in science, when you introduce something, like a conversion factor, you need to be able to quantify it. And you need to be able to define it in a very specific way. And here's the definition. So the counting unit, we are introducing a so-called counting unit that is called mole. What does it mean? What is a mole? A mole is the amount of substance that contains as many particles as there are in 12 grams of carbon-12. And why is it compared now to carbon-12? Could you imagine why?
Because
Based on the previous lectures that we had so far. Sorry? Simple? Well, I know. Simple in what terms?
It's exactly 12 U's.
to know the mass.
Yes, it's because it's exactly 12 U's. Meaning that we know the standard of the carbon was introduced because regarding the atomic weight of a single carbon atom was because they were able to determine the mass of the single carbon atoms with the best precision. The simplest one would have been hydrogen, but they were not able to determine the mass that precisely and accurately. So that's why they chose the standard of carbon. And we have introduced that when we talked about the atomic mass. The atomic mass of carbon 12 is 12U. Now this 12 comes back here. So we say everything that has the same amount of particles as there are in 12 grams of this substance, carbon 12. This number of particles is called, is a new group. This is what we call a mole. So in this picture here, we have 518 grams of lead. That contains 2.5 mole, meaning that it contains 2.5 times more lead atoms than there are in 12 grams of carbon 12. Okay, let's look a little bit into more detail. Let's say you have a table. You have a single carbon atom. What is the mass of that atom? It's defined. It's 12 atomic mass units. What is that in grams? Well, you need to know the conversion factor, and that's here. That's the mass in atomic mass units, and this is the mass in grams. So here, this is the conversion. 1U is 1.661 times 10 to the power minus 24. If you have 12U, you have 12 times that. And that's the mass of a single carbon 12 atom in grams. It's very light because you have a 10 to the power minus 23. The first digit is at the 23rd position after the decimal. To the right of the decimal. Okay? So but that's because it's just a single carbon atom. Now, if we have 1,000 carbon atoms, what is the weight of 1,000 of this group of 1,000 carbon atoms?
12 times 25.
Well, it's 12,000 U, right? 12 times 1,000. 1,000 times 12U. It's 12,000 U. This is just in a different notation. Let's look the one in grams. So you have 1,000 carbon atoms times the mass of a single carbon atom. That is given here. So 1,000 times the mass of the single carbon atoms gives you the mass of 1,000 carbon atoms. You see the exponent changed from minus 23 to minus 20. So now the first digit is not at the 23rd position, but it's in the 20th position. So we're getting closer to the zero as we increase the number of atoms, right? Makes sense. If we have 1 million carbon atoms, what is the weight in atomic mass units? Well, you have 1 million times the mass of a single carbon atom. That's 12 million U. In grams, the exponent increased by another factor of 3 to minus 17. So the first digit is at the 17th position, so it's getting closer to the decimal. Let's say you have now 12 grams of carbon. Now here this is the mass of 1 million carbon atoms. Now the question is, how many atoms do we have here? If we have 12 grams. The 12 grams is now something that we can measure actually in a lab. We cannot do measurements in this order of magnitude. There's no scale that can give you this precision, give you answers for numbers that are at the 17th or 20th digit after the decimal. There's not such a scale. But what we can do in the lab, there are scales where you can weigh in substances that are in the grams or kilograms or milligrams, micrograms region. So what is, and there's another reason why I'm interested in the number 12 and not 20. But let's look first just at this number 12. This number 12. So how many atoms do we have in 12 grams? You have to weigh in. So there must be a lot of carbon atoms, right, to accumulate to this 12 grams. If you have this tiny fraction, this tiny amount, you know that there are 1 million. So if you have 12 grams, how many times is that bigger than that? 10 to the 20. No, 20? Yeah.
12 to the 23.
10 to the power of 18, something like that. 10 to the power of 18, 1 with 18 zeros higher. Well, you can get this number now, because you know the number or the mass of a single atom. In grams, you know it in grams, and you know it in atomic mass units. So you simply divide 12 grams by this number here, which is the mass of a single carbon. If you have 12 grams of the whole group, of a big group, you don't know how many, you want to calculate that, divided by the mass of a single one, you get the number, how many of them accumulate to this mass. And that is this number. 12 divided by this gives you this number here. And this number, you will work with it over the course of the semester. What is this number called? This is Avogadro's number. So this group, and a group, any group that contains exactly this number of atoms or particles, whatever it is, baseballs. If you have this amount of baseballs, then you have a mole of baseballs. Yeah.
What do you call that number again?
Avogadro's number. It will come again. Okay. So any group of atoms, this group of atoms, or not only atoms, actually I should write here particles. Can be any particle. This group of particles has a special name, and that is called mole. So anything that has 1 mole, you know it has this many particles in there. As you know, when I say how many particles are in a dozen of particles? In a dozen. How many particles are there? 12. A dozen of particles have 12 particles. Right? A dozen atoms are 12 atoms. So you have a specific name for this number 12. This number 12 is connected, you have a specific name that is called dozen. Here, this number has also a name that is called mole. Any group that contains this many atoms or particles is called a mole. So it's defined by carbon. And this concept was introduced and it's called Avogadro's number because it's named after Amadeo Avogadro. Actually, this guy has, I don't know, there are 6 other names in between here. I just wrote the first and the last one. Amadeo Avogadro lived 18th to 19th century. And this is his number, Avogadro's number. So there's Avogadro's number, so this number of particles in a mole of any substance. That's the definition of this number. If you have a mole of baseballs, there are 6 times 10 to the power of 23 baseballs in that group. Well, there are no such many baseballs, of course. But if you have half, and what does it mean if you have half a mole of particles? What is the number of particles then? This number divided by 2. If you have 2 moles of particle, then it's this number multiplied by 2. If you have 10 moles of particles, then it's this number times 10. Okay? So, this number, this is the amount of atoms contained in 12 grams of carbon-12. So you have carbon-12 substance on your scale, you have exactly 12 grams, you know that there are this many carbon atoms in there. Because we know the mass of each carbon atom. If you wouldn't know the mass of each carbon atom, you wouldn't know this number. Right? 12 grams divided by the mass of a single atom gives you the number of atoms in that group. Alright. So the concept of mole is defined so that we may equate the amount of matter to the number of particles. So in this way you have now a connection between mass of a substance and the number of atoms of the substance. And why is that important that we can translate that? Because in the chemical reaction, it's not the mass that is important, but it's the number of atoms that are important, how they are combining. Because the masses of atoms are different. You can have heavy atoms and light atoms. What is important is how many atoms you are combining with how many other atoms. That's why you need a conversion from mass that you can measure in your lab on the scale. You need a conversion to the number of atoms. And Avogadro's number gives you that conversion, that possibility to determine from the mass that you can measure the number of atoms or number of particles. So that's what it says here. We have now something that equates the amount of matter in terms of mass to the number of particles in terms of mole. That we just defined what a mole is. And the standard is based upon C12 isotope. And the reason is because the precision, the ability to precisely measure the mass of a single carbon atom, of a single carbon-12 atom. The mass of one C12 atom is this, and the mass of 12 grams, of a mole of carbon-12 is 12 grams. So this is atomic mass in units. This gives you just again what the conversion factor, what atomic mass units is in grams or kilograms. Now, why did we pick 12? Why did I ask? We could have also say, let's pick 16 grams of oxygen, of carbon. Or let's pick 200 grams of carbon and look how many atoms are in 200 grams, and let's define that number of atoms as being the Avogadro's number. Sorry? Yes. Atomic number, you said?
Atomic mass.
The atomic mass, yes, atomic mass. That's right. Let's look at this table now. What do I have here? We have here the mass of carbon, and this is the mass of oxygen. I just picked oxygen. I could have taken also any other arbitrary number because I want to compare their relative masses to each other. So if you have a single carbon atom and a single oxygen atom, you see in atomic mass units, this is the weight of a single carbon, this is the weight of a single oxygen. Their ratio of mass of oxygen to the mass of carbon is 16 divided by 12 is 1.33. Meaning that an oxygen atom is 1.33 times heavier than a carbon atom. So 33% heavier. So that's when you compare a single oxygen to a single carbon. What if you have 1,000 oxygens here and 1,000 carbons here? Well, here are the masses. We have 1,000 carbons here. Both of them, you divide the mass of 1 million oxygen by the mass of 1 million carbon, you get still the same ratio. How about if you have now, instead of 1 million, now we have 1 mole of each? Well, 1 mole of means that there are 6 times 10 to the power 23 carbon atoms. And also the same number of oxygens. That's the definition. You have 1 mole of carbons and 1 mole of oxygens. The ratio must be the same. We just increased in both the same number of atoms, of oxygens and of carbons. Correct? So the ratio must be still the same. So what is the mass then of the oxygen if you have 1 mole of oxygen? It's 16 grams per mole. If you look at the periodic table, what is the atomic mass of oxygen? It's actually given here, it's 16. That's what he said. So what you have there, 16 U, that's the mass of a single oxygen, and the mass of 1 mole of oxygen is 16, it's the same numerical value, 16 grams per mole. So in the periodic table, when you see the atomic masses, that's the mass of a single atom of that element. But it's also the mass of a mole of that element in grams per mole. It's the same value. It's the same numerical value. So that's why we chose 12 grams of carbon, because we are keeping the relative ratios of the masses to the other elements the same. Okay, so the ratios are always, you compare oxygen to carbons, you compare one atom, one single oxygen, the mass of one single oxygen to the mass of a single carbon atom, the difference is 1.33. You compare the mass of 1 mole of oxygen to the mass of 1 mole of carbon, you get that's still the same ratio. Because the molar mass, this is called molar mass, is the same as the numerical factor is the same. 16. It's just the unit is different. And that is called molar mass of oxygen. This is the molar mass of carbon. Since we can, now that explains why we used 12 grams and not 250 grams or 1 million kilograms of carbon. So we want to be very practical and keep the relative masses of the various elements in the periodic table the same to each other. Their ratios should remain the same. So since we can equate mass, so how much matter, with moles, how many particles, so one mass is given in grams, or is given in grams, whereas the other one is given in number of particles, we now have a conversion factor that relates the two. What is the conversion factor? Well, that's moles times the molar mass. That gives you grams. So you know the molar mass of each element. It's given in the periodic table. And if you have a number of moles, you get grams, the mass of your substance. And vice versa. If the grams is given to you, you put it on your scale. You have a substance, you put it on a scale, you know the mass. If you know what kind of element or compound it is, you can determine the molar mass because you have the periodic table. So then you have grams and molar mass, and you can calculate how many moles. And if you know how many moles you have, you also know how many particles there are, because each mole contains 6.02231 times 10 to the power of 23 particles. So the molar mass of a substance is the amount of matter that contains 1 mole or 6.022 times 10 to the power of 23 particles, aka Avogadro's number. So the atomic mass on the periodic table also represent the molar masses of each element in grams per mole. Okay? That's what is given in the periodic table. So when we compare here now we are comparing 1 mole amounts. Each beaker contains 1 mole of that substance, the corresponding substance. This contains 1 mole of sulfur, this contains 1 mole of magnesium, 1 mole of tin, 1 mole of silicon, 1 mole of copper. The weights are different because each atomic mass is different. Sulfur is heavier than, each sulfur atom is heavier than each magnesium atom. This is even heavier than the other two. This is relatively light. This is 63. And therefore, because each atom weighs differently, the molar masses are also different if they contain the same number of atoms. If the number of moles is the same, that means that there are everywhere here is the same number of atoms. So we have the same number of sulfur atoms here as there are magnesium atoms here, as there are tin atoms here, silicon atoms here, and copper atoms here. So you have the same number of atoms, but because the weight of each atom is different, so depending on the element, you have also a different weight. So 1 mole of sulfur weighs 32.066 grams. That's the number that is given in the periodic table. 1 mole of magnesium weighs 24 grams. That's lighter than this. 1 mole of tin, even though it looks like a smaller amount, but it's actually heavier. It's 180. It's almost 4 times heavier than sulfur. Silicon, slightly heavier than magnesium, lighter than sulfur. Significantly lighter than tin. This is copper. Alright, so you have different elements, they have different masses, but if you have the same amount, here the same amount is 1 mole, you have different masses of those moles, and the masses are exactly the same as the atomic masses, just in different units, in grams. If it's in moles, then it's in grams. If it's individual atoms, then it's the atomic mass unit. So the molar mass of an atom is a conversion factor that relates mass to moles and vice versa. Mass tells you how much matter you have, and moles tells you the number of atoms or number of particles. So mass times the molar mass gives you the number of moles. This is how you calculate it. If you have a substance, you weigh it on a scale, you know the mass, you multiply it with the molar mass, you get the number of moles. Grams times moles per grams gives you the number of moles. Avogadro's number then relates, so you get the number of moles, you know that 1 mole contains Avogadro's number of particles. So if you have half a mole or 0.1 mole, so you have just this number times Avogadro's number, that gives you the number of particles. So 1 mole, there are this many particles in 1 mole, so this is the number of particles that is in 1 mole. This summarizes it again. So, if you have this is an example. If you have 16.5 grams of carbon, you divide it by the molar mass of carbon, you get the number of moles. This is the amount of moles. 1.37 moles of carbon. How many particles are there in 1.37 moles of carbon? How would you calculate that?
That times the number.
Times Avogadro's number.
Avogadro's number, yeah.
That number times Avogadro's number gives you the number of carbons that are contained in 16.5 grams of carbon. You need to, so this one here, you just take, if the mass is given, the molar mass is always given to you as long as you have the periodic table in your hand. So, which I will provide, including the molar masses. So you divide this by this and you get the number of moles. Now, let's practice this a little bit. So how many magnesium atoms are there in 150 grams of magnesium? So you have 150 grams of magnesium. That was actually the first image that I showed you, the magnesium solid, magnesium metal. So you have 150 grams of magnesium. And now the question is, how many magnesium atoms are in 150 grams? How do you calculate that? You calculate first the number of moles. So how many moles of magnesium you have. And then, once you know that, you can calculate by just multiplying that number of moles with Avogadro's number, you get the number of magnesium atoms. So how do we calculate the number of moles? 12.5 moles? Let's see. So you have 150 grams of magnesium. How do we translate that now into the numbers of moles?
150.0 grams.
You divide it by the molar mass of magnesium, right? You divide this by the molar mass of magnesium. What is the molar mass of magnesium? It's given in the periodic table. It's around 24 something, right? So 1 over 24, you divide it by 24.305. This number is given in the periodic table. That will give you the number of moles. So 150 divided by 24. What did you say? How many moles is this? 6?
6.25.
6.25? So this will give you 6.25 moles. You multiply it by Avogadro's number to get the number of atoms. This is the number of atoms. This is done here now in a single step. You can do it also in 2 steps. You do first this, you get the number of moles, and then you multiply that with this, you get the number of atoms. And this is just a side note regarding the significant figures. And that's a big number. You need to be aware of what this means. 10 to the power of 24 plus 24. It's a huge number. There's no name for that number. So what amount of magnesium is represented by 0.2 grams? How many atoms? Again, magnesium has the smaller mass. So now you just divide 0.2 grams divided by 24. Now you get 8.23 times 10 to the power of minus 3 moles. So this is a tiny fraction of a mole. About 1,000 or 100 times smaller than a single mole. So therefore you will have less than Avogadro's number of particles, right? Because it's a fraction of a mole, indicated here by 10 to the power minus 3. So how many atoms do we have in a piece of magnesium? If you have only 0.2 grams of magnesium. How do we calculate it?
Avogadro's number divided by 8.22.
Yes, Avogadro's number, but multiplied by this. Multiplied. So this times Avogadro's number gives you the number of atoms. So here you see we have now something with 10 to the power of 21. Look at this, compare this to this number. It's smaller. Well, you have a smaller mass, much smaller than the molar mass. In this mass of magnesium, you have this amount of atoms. You have now a much smaller mass, so you must have also smaller number of atoms. Yeah?
When you write in the mass, you always look for significant figures. You have 24.31.
So regarding the significant figures, the rules of the textbook, and we use this rule here. You use always one more significant figure than the one that is given to you in terms of the mass. Because here in the periodic table, there could be maybe sometimes 5 significant figures. But you use only one more than the one that is given to you to do the calculation. It's a good question. So here you have 3, that's why we use 4 significant figures. Okay, I think we can do this next time. Next Tuesday we'll continue with this.